Imagine standing on Mars, a pale blue dot, Earth, distant in the alien sky, a third the size of the full moon, up to 140 million miles away. This is the defining challenge of our era, requiring innovation to survive the 9-month journey across 300 million kilometers of void, endure isolation in cramped habitats, and thrive on a world inhospitable to humans, with temperatures as low as 195 degrees, 126 degrees, and no shield from solar radiation or dust. Storms. Every story like this begins quietly. Just a strange light, a missing piece, a question no one wants to ask. If you feel that same tension, that pull towards something we're not supposed to see, hit like, subscribe, and comment your thoughts. And if you want others to join us on this journey, share the video, X, Facebook, Reddit, anywhere you can. You're the reason stories like this reach beyond the algorithm. Thank you for being awake. Mars has long captivated scientists, engineers, and dreamers, but reaching it demands solving interconnected problems: distance, radiation, fuel, biology, and engineering. Every system, from life support to propulsion, must work flawlessly, or explorers risk being stranded. Private companies like SpaceX and NASA are pushing technological frontiers to make interplanetary travel a reality and secure humanity's future. Time may be the greatest obstacle. Political uncertainties, economic pressures, and climate change are narrowing the window for a crewed mission. Rising seas, extreme weather, and resource depletion threaten to destabilize societies and shift focus away from space exploration. Mars missions require constant maintenance and resupply from Earth, making delays costly as technology ages and funding wavers. With each passing year, the risk of losing momentum and expertise grows. The question is not just can we go to Mars, but will we go in time? The clock is ticking louder every day, echoing through the Martian plains where rovers like Curiosity and Perseverance already pave the way, sending back data and haunting images of a world waiting to be explored. Section 1. The clock is ticking. Mars orbits the Sun at a different speed and distance than Earth, making it a moving target. Currently, you're 140 million kilometers away. Its distance constantly changes. Every 26 months, Mars comes within 55 million kilometers of Earth. Miss this window, and the journey becomes vastly more challenging. During the 2003 opposition, Mars was closer to Earth than it had been in nearly 60,000 years, at 55.8 million kilometers. Even then, the travel distance is enormous, comparable to circling Earth over 200 times. An optimal launch window still means a 6 to 7 month journey. This means 6 months in deep space, beyond Earth's protective magnetosphere, exposed to cosmic radiation and solar storms. Astronauts on the ISS receive about 10 times the radiation experienced on Earth. A Mars mission could expose them to up to 700 times more. 6 months in microgravity also leads to bone and muscle loss, with astronauts losing 1 to 2% of bone mass per month despite exercise. And that's just one way. The mission involves the journey to Mars, the surface stay, and the return, totaling nearly 900 days, 2.5 years away from Earth. During this time, real-time communication with Earth becomes impossible, with signals taking between 3 and 22 minutes to travel. The psychological toll of isolation and confinement is unprecedented. The first challenge is escaping Earth's gravity, requiring a velocity of 11.2 kilometers per second or over 40,000 kilometers per hour. The Saturn V rockets, which sent astronauts to the Moon, lacked the power to send humans directly to Mars. Mars represents a potential future home for humanity, a backup plan if Earth becomes uninhabitable. Could the biggest rocket ever built be our ticket to Mars? Section 2. The rocket equation. Reaching Mars requires a massive rocket to escape Earth's gravity. The rocket equation, formalized by Konstantin Tsiolkovsky in 1903, is brutally simple. For every kilogram of payload, you need many kilograms of fuel. Tsiolkovsky's equation, dv v ln mo mf, underpins every space mission where dv is the change in velocity, va is the effective exhaust velocity, mo is the initial total mass, and mef is the final mass after burnout. The Saturn V, for example, had a payload capacity of just 3% of its total mass. This exponential problem is the tyranny of the rocket equation, a mathematical barrier that has limited human spaceflight for over half a century. Every mission to the Moon, Mars, or beyond must grapple with this fundamental constraint. SpaceX's Starship is designed to overcome this challenge. A two-stage, fully reusable system, it stands 121 meters tall and weighs roughly 5,300 metric tons when fueled. The Super Heavy booster, powered by 33 Raptor engines, produces over 73.5 meganewtons of thrust, equivalent to the power of 18 million horses. The booster's stainless steel construction, chosen for its resilience in extreme temperatures, endures the inferno of liftoff and re-entry. Starship's upper stage, with 6 additional Raptor engines, can deliver 150 metric tons to low Earth orbit, a significant leap from the Falcon 9's 22.8 metric tons. This capacity opens the door to launching massive payloads such as habitation modules, scientific instruments, or even infrastructure for off-world colonies. However, a fully fueled Starship lacks the propellant to reach Mars. The journey requires a delta V of approximately 15 kilometers per second, far exceeding the 9.4 kilometers per second needed for low Earth orbit. To solve this, SpaceX proposes orbital refueling, launching a crew vehicle to orbit, followed by tanker starships that dock and transfer fuel. Each tanker, carrying up to 200 metric tons of propellant, would refuel the crew vehicle in a delicate ballet of precision engineering. This process, requiring up to 16 tanker flights, is complex and untested but essential for Mars missions. Success would enable Starship to carry enough fuel to accelerate to Mars velocities, decelerate into Mars orbit, and later return to Earth, a round trip spanning hundreds of millions of kilometers. Orbital refueling marks a departure from traditional space exploration. It demands precision, reliability, and multiple successful launches in rapid succession. Each refueling operation involves coordinating the rendezvous of 2 massive orbiting spacecraft, transferring cryogenic methane and oxygen propellants, and ensuring no leaks or explosions occur. If it fails, the Mars mission architecture could collapse. If it succeeds, it would revolutionize spaceflight, enabling missions beyond Mars. SpaceX plans to demonstrate this technology soon, but until it's proven, the risks remain high. The company's 2022 attempt to catch a Starship prototype with mechanical arms hinted at the challenges ahead, a feat that, if perfected, could enable rapid reusability and refueling in orbit. If refueling succeeds, the next hurdle is surviving the 6 to 9 month journey to Mars. Hazards include radiation, micrometeoroids, and psychological stress. The spacecraft must shield the crew from cosmic rays and solar flares which can cause cancer, cataracts, and cognitive decline. Life support systems must recycle air, water, and waste with near-perfect efficiency, as resupply or rescue would be impossible during transit. Any failure in these systems could be catastrophic. For example, a micrometeoroid strike could puncture the hull, causing rapid decompression, while a solar flare could cripple electronics and expose the crew to lethal radiation doses. Observation: SpaceX's Starship program is unprecedented in scale. Its Starbase facility in Boca Chica, Texas operates 24/7, with hundreds of workers building and testing prototypes at breakneck speed. Since 2019, SpaceX has rapidly iterated on full-scale Starship designs, reflecting the urgency of its ambition to make humanity multiplanetary. As of 2023, over 20 prototypes have been built, tested, and often destroyed in spectacular explosions, each failure providing invaluable data. The most dramatic test occurred in 2021 when Starship SN-15 soared 10 kilometers into the sky, flipped horizontally, and landed intact, demonstrating the vehicle's unique belly flop maneuver. Interpretation: the rocket equation is both a technical and philosophical challenge. It represents the struggle to overcome Earth's constraints and reach the cosmos. Starship, with its orbital refueling strategy, aims to break this barrier. Success could make space travel routine and accessible, but the risks and uncertainties are immense. For instance, the Apollo program, which sent humans to the moon, was constrained by the rocket equation. The Saturn V's limited payload capacity meant astronauts could only stay on the lunar surface for days, not weeks or months. Starship, if successful, could enable long-term habitation on other worlds, transforming humanity from a single-planet species to a multiplanetary one. Speculation: if orbital refueling becomes routine, it could enable permanent human settlements on the Moon, Mars, and beyond. SpaceX envisions starships ferrying people and cargo across the solar system, creating self-sustaining colonies. This future hinges on mastering the rocket equation, a challenge that has defined space exploration from the start. The stakes are monumental, and the outcome remains uncertain. As Elon Musk himself has said, the future will be vastly more exciting if we're a spacefaring civilization and a multiplanetary species than if we're not. The question is whether Starship can solve the rocket equation and unlock the cosmos for humanity, or whether the tyranny of the equation will keep us bound to Earth. Section 3, the hostile void. Deep space is not empty. It's teeming with invisible dangers, a silent battlefield where unseen forces threaten the very fabric of human biology. Outside Earth's protective magnetosphere, the crew is exposed to two primary sources of radiation: galactic cosmic rays and solar particle events. Galactic cosmic rays are high-energy particles originating from outside our solar system, accelerated by supernovae and other cataclysmic events. They consist mostly of protons, about 85%, but also include heavier ions like iron, 1%, and carbon, 0.3%. These particles travel at nearly the speed of light, some possessing energies exceeding 10 times to 20 electron volts, far greater than anything produced in particle accelerators on Earth. They can penetrate deep into matter, including human tissue, leaving a trail of ionization and cellular damage in their wake. The estimated radiation dose for a 3-year Mars mission is approximately 900 millisieverts. 300 times the average annual radiation dose on Earth, which is about 3.1 millisieverts. Exposure at this level significantly increases the risk of cancer, cardiovascular disease, cataracts, and cognitive decline. Apollo astronauts, who spent only a few days outside Earth's magnetosphere, reported seeing flashes of light when they closed their eyes, a phenomenon attributed to cosmic rays interacting with their retinas. Animal studies show that exposure to high-energy particles causes changes in brain structure. Neurons lose dendritic complexity, reducing their ability to communicate with other neurons. Synaptic density decreases, impairing the brain's capacity to form and store memories. Memory and decision-making are impaired, with some tests showing a 20% reduction in cognitive performance after 6 months of exposure. Some researchers estimate that 1 in 5 astronauts on a long-duration Mars mission would experience measurable cognitive decline, a sobering statistic for a mission that requires peak mental acuity. Solar particle events are different. These are bursts of radiation released during solar flares and coronal mass ejections, which can expel up to 10 billion tons of plasma into space at speeds exceeding 1 million miles per hour. They consist mostly of lower energy protons, around 10 to 100 million electron volts, but come in enormous quantities, sometimes exceeding 10 billion protons per square centimeter. A large solar particle event can deliver a lethal radiation dose in a matter of hours if the crew is unprotected. The largest recorded solar particle event in 1972 would have been fatal to astronauts in deep space, delivering a dose of over 4,000 millisieverts in just a few hours. The good news is that solar particle events are somewhat predictable. They occur more frequently during solar maximum, the peak of the sun's 11-year activity cycle, and monitoring systems can provide some warning. NASA's Solar Dynamics Observatory and the ESA's Solar Orbiter are among the spacecraft constantly watching the sun, providing early detection of solar flares and coronal mass ejections. However, the bad news is that no amount of warning helps if you don't have adequate shielding. Traditional shielding materials like lead or aluminum are heavy and not particularly effective against high-energy particles. In fact, when high-energy particles strike heavy materials, they can produce secondary radiation through a process called spallation, creating a cascade of neutrons and other particles that's even more dangerous than the original radiation. So current research focuses on lightweight shielding materials with high hydrogen content, things like water, polyethylene, or advanced materials like hydrogenated boron nitride nanotubes. These materials are better at absorbing radiation without producing harmful secondary particles, as hydrogen's low atomic number reduces the likelihood of spallation. The Starship design includes some radiation protection, with plans to use liquid methane and oxygen in the propellant tanks as a makeshift shield. However, it's unclear whether it will be enough for a Mars mission. Additional shielding may need to be added, increasing the vehicle's mass and complicating an already challenging engineering problem. Another option is to use supplies as shielding. Water, food, and equipment could be arranged around sleeping quarters to create a radiation shelter, a strategy known as point shielding. But even with shielding, the crew will still receive a significant dose. A round-trip Mars mission would expose astronauts to roughly 60% of the career radiation limit recommended by the National Council on Radiation Protection and Measurements. NASA's current career exposure limits for astronauts allow for a 3% increase in lifetime cancer risk, a threshold based on studies of atomic bomb survivors and radiation workers. A Mars mission would exceed those limits. So the question becomes, is the risk acceptable? There's no easy answer. To put it in perspective, a 3% increase in cancer risk means that for every 100 astronauts who go to Mars, 3 additional cases of cancer would be expected over their lifetimes. But the true risk may be higher, as radiation in space is more energetic and complex than Earth-based sources, and its long-term effects are not fully understood. Even if we mitigate the radiation risk, there's another challenge waiting on Mars itself: landing. How do you land a 100 metric ton spacecraft on a planet with almost no atmosphere? The Martian atmosphere is just 1% as dense as Earth's, offering little resistance to slow a descending vehicle. Without a thick atmosphere to rely on for aerobraking, engineers must design a propulsive landing system that can gently lower the spacecraft to the surface. The challenge is daunting: a controlled explosion perfectly timed and executed to bring the spacecraft to a safe touchdown. Section 4. The Thin Red Line. Getting to Mars is one thing. Landing on Mars is something else entirely. The challenge is the Martian atmosphere. It's thick enough to cause heating and drag during entry, but not thick enough to slow a spacecraft down for landing. On Earth, parachutes work well because the atmosphere is dense. On Mars, the atmosphere has less than 1% the density of Earth's. A parachute can help, but it's not enough. Previous Mars landers and rovers have used a combination of heat shields, parachutes, and retro rockets to land safely. The Mars exploration rovers Spirit and Opportunity each weighed around 185 kilograms and used parachutes along with airbags to cushion their impact on the surface. The larger Curiosity rover, weighing nearly 900 kilograms, employed a sky crane system, where a rocket-powered descent stage lowered the rover on tethers before flying away to crash land elsewhere. But these were modest compared to what's coming. Starship, by contrast, has a mass of approximately 100 metric tons when empty and significantly more when carrying crew and cargo. That's 100 times heavier than anything we've ever landed on Mars. The thin atmosphere cannot slow it down sufficiently through aerodynamic drag alone, so the spacecraft must use its engines to decelerate. This is called supersonic retropulsion. The spacecraft fires its engines while traveling at supersonic speeds through the atmosphere, creating thrust in the direction of travel to slow down. Until recently, engineers weren't sure this would work. Firing engines backward while moving through an atmosphere at high speed creates a shockwave that moves unpredictably. It could potentially damage or destabilize the vehicle. But SpaceX has been testing supersonic retropulsion with its Falcon 9 rocket boosters, which use the same technique to return to Earth and land vertically after launching payloads to orbit. Those tests have been successful. The data shows that the shockwave actually forms a protective bubble around the vehicle, insulating it from buffeting and reducing heating. This is promising. It suggests that supersonic retropulsion at Mars is feasible, but there are still challenges. The temperatures generated during entry can exceed 1,600 degrees Celsius, hot enough to melt steel. The heat shield on the Starship must withstand these conditions without failing, as any breach would be catastrophic. Mars has unpredictable winds and dust storms. Landing accuracy is critical. The vehicle needs to land on relatively flat terrain, free of large rocks or slopes that could tip it over. Current technologies can land a spacecraft within an ellipse of about 20 kilometers. That's good, but not good enough for a crewed mission where the landing site must be carefully chosen. So new navigation technologies are being developed. These include terrain relative navigation, which uses cameras and sensors to identify landmarks during descent and adjust the trajectory in real time. The goal is to land within a few hundred meters of the target. Even with perfect navigation, the landing itself is risky. The engines must fire at precisely the right time. Too early and the spacecraft runs out of fuel before reaching the ground. Too late and it crashes. The margins are razor thin. Timing is everything. During the final seconds of descent, the spacecraft must transition from supersonic to subsonic speeds, a phase known as transonic flight, where aerodynamic forces are particularly unstable. Miscalculate here, and the vehicle could tumble out of control. But landing is just the beginning. Surviving on Mars is the next test. The red planet is a hostile environment, with temperatures plummeting to 125 degrees Celsius at night and rising to a frigid 19 degrees Celsius during the day. The atmosphere is primarily carbon dioxide, offering no breathable air for humans. Radiation levels are dangerously high, as Mars lacks a global magnetic field like Earth's to deflect solar and cosmic radiation. Dust storms can rage for weeks, sometimes engulfing the entire planet and blocking sunlight, as occurred in 2018 when a global dust storm shut down the solar-powered Opportunity rover permanently. Any human outpost would need robust systems to filter dust, generate oxygen, recycle water, and grow food in controlled environments. The psychological toll of living in such isolation, millions of kilometers from Earth, cannot be underestimated. Could the red planet ever feel like home? The first crews will face challenges unlike any other in human history. They will need to adapt to a world where the sky is pink at sunset due to scattered light from fine dust particles, where the gravity is just 38% of Earth's, and where the harsh beauty of the landscape is both awe-inspiring and unforgiving. Success will depend on technology, ingenuity, and resilience. The thin red line between survival and disaster is perilously fine, but it is a line humanity may one day cross. Section 5. The frozen desert. Mars is cold. Surface temperatures range from about 125 degrees at the poles during winter to 23 near the equator during summer. The average temperature is around 60 degrees, making it comparable to the coldest deserts on Earth, such as the Antarctic dry valleys, where temperatures can plummet to 89 Nelson. The Martian atmosphere is a stark contrast to Earth's, consisting mostly of carbon dioxide 96%, with traces of nitrogen 1.9%, argon 1.9%, and a negligible amount of oxygen 0.146%. This composition renders the air both unbreathable and incapable of providing the insulation needed to retain heat, resulting in wild temperature swings. During the Martian day, temperatures can soar to a balmy 20 degrees, only to plummet to 70 degrees at night, a fluctuation that would freeze any exposed water in minutes. A human exposed to the Martian environment would lose consciousness within 15 seconds and die within 90 seconds. The atmospheric pressure on Mars is a mere 0.6% of Earth's sea level pressure, equivalent to the conditions at an altitude of 35,000 meters on Earth, almost 4 times higher than the summit of Mount Everest. This low pressure causes water to boil at just above 0 degrees C, making it impossible for liquid water to exist on the surface without protection. The crew, therefore, needs a habitat, a pressurized environment where they can live and work, shielded from the relentless cold and the near-vacuum conditions outside. Early concepts for Mars habitats involve landing a module ahead of the crew, which would deploy automatically, inflate or unfold and prepare itself for habitation. This module must provide everything the crew needs: breathable air, drinkable water, food, temperature control, radiation shielding, and waste processing. It must also be entirely self-sufficient. There's no emergency rescue, no resupply missions. If something breaks, the crew has to fix it themselves. The habitat must withstand Martian dust storms, which can last for weeks, blocking sunlight and coating surfaces with abrasive dust particles. During the 2018 global dust storm, NASA's Opportunity rover lost power entirely and never recovered. Such storms are a constant threat to power systems, habitats, and crew safety. One way to reduce risk is to use local resources. This is called in situ resource utilization, or ESRU. Mars has resources that can be harvested and processed to support the crew. The atmosphere is mostly carbon dioxide, which can be captured and processed to produce oxygen for breathing and methane for fuel. Water ice exists on Mars, buried beneath the surface in many regions, particularly near the poles. Radar data from NASA's Mars Reconnaissance Orbiter has revealed vast deposits of water ice as little as 1 meter below the surface in some areas. If the crew can access it, they can melt it, purify it, and use it for drinking, hygiene, and agriculture. The soil, or regolith, contains minerals like iron oxide, aluminum, and silicon, which could be used for construction or manufacturing. But harvesting these resources requires specialized equipment: drills, excavators, chemical processing plants, power systems. All of this must be designed, tested, and transported to Mars. And it all must work reliably in an environment where temperatures swing wildly, dust storms are common, and there's no one to call for help. NASA is currently developing ISRU technologies. A small experiment called MOXIE was sent to Mars aboard the Perseverance rover in 2021. MOXIE demonstrated that oxygen can be produced from the Martian atmosphere. It successfully converted carbon dioxide into oxygen multiple times, producing about 6 grams of oxygen per hour, enough to support a single astronaut for a few hours. A scaled-up version of MOXIE could produce enough oxygen to support a crew and provide propellant for a return vehicle. But scaling up is not trivial. A full-scale system would need to produce approximately 25 metric tons of oxygen over the course of a year and a half. That requires a lot of power and robust equipment. The system would need to operate continuously, withstanding extreme temperatures, dust, and radiation, without human intervention. And power is the next hurdle. Producing enough propellant for a Mars ascent vehicle will require a power system capable of generating several hundred kilowatts continuously over a period of 500 days. That's far more power than any spacecraft has ever produced. So what's the power source? 2 main options are being considered: solar panels and nuclear reactors. Solar power is appealing because it's proven technology. Photovoltaic panels are lightweight, reliable, and don't require complex machinery. But Mars is farther from the Sun than Earth, so solar panels produce less power. They're also affected by dust, which accumulates on the panels and reduces efficiency. A recent analysis suggests that for landing sites near the Martian equator, solar power could be viable, especially if supplemented with hydrogen fuel cells for nighttime power. But at higher latitudes, where sunlight is weaker and dust storms are more frequent, nuclear power may be necessary. NASA has been developing small nuclear reactors called kilopower units. These reactors use uranium fission to generate heat, which is then converted into electricity. A single kilopower unit can produce about 10 kilowatts continuously, day or night, regardless of weather. For a Mars mission, several kilopower units could be linked together to provide the necessary power. The challenge is mass. Nuclear reactors are heavy, and so is the shielding required to protect the crew from radiation, but they're also reliable, and on Mars, reliability matters more than efficiency. A failed power system could mean the end of the mission, as there are no backup options. The kilopower system has been successfully tested on Earth, operating for 28 hours straight in a simulated Mars environment. However, transporting such a system to Mars and ensuring its operation over years, not hours, remains a significant engineering challenge. But even if we solve the power problem, there's another fundamental need: food. Can we grow crops on a planet where nothing has ever grown before? Mars lacks the rich, organic soil found on Earth. Its regolith is sterile, devoid of life, and contains perchlorates, toxic chemicals that could harm both plants and humans. Any farming system would need to be entirely self-contained, using hydroponics or aeroponics to grow plants in a nutrient-rich solution or mist. The habitat would need advanced LED lighting systems to simulate sunlight, as Mars receives only about 43% of the sunlight Earth does. Growing enough food to feed a crew would require significant resources, including water, nutrients, and power. A single crew member would need approximately 0.8 kilograms of food per day, or about 292 kilograms per year. For a crew of 4 on a 2-year mission, that's over 2,300 kilograms of food. Observation. The Martian environment is not just unforgiving, it actively works against human survival. Every system, habitat, power, food production, must be designed to function flawlessly in conditions that push the limits of engineering. There is no room for error, no margin for failure. The stakes are unimaginably high. Interpretation. The challenges of living on Mars are not merely technical, they are existential. To survive there, humans must create a bubble of Earth-like conditions, a fragile oasis in a hostile world. This requires not just technology, but a deep understanding of how life interacts with its environment. Speculation. If humans ever colonize Mars, it won't be because we conquered the planet. It will be because we learned to live within its constraints, to adapt to its rhythms and to respect its unyielding nature. Mars will not be tamed, but it might, just might, tolerate our presence. Section 6. The Martian Greenhouse. The crew needs to eat. A human requires approximately 2,000 to 2,500 calories per day, depending on activity level. Over the course of a 900-day mission, each crew member will need roughly 2 million calories. That's a staggering amount of food. Prepackaged meals from Earth could work, but they take up valuable space and add significant mass to the payload. For example, a single crew member's food supply for the mission could weigh over 700 kilograms, a logistical nightmare. And after a year or two, the crew will be desperate for variety. Psychological studies show that monotonous diets can lead to decreased morale, increased stress, and even depression among astronauts. So researchers are developing ways to grow food on Mars. The concept is called bioregenerative life support. Instead of relying entirely on stored food, the crew cultivates crops inside a pressurized greenhouse. The plants consume carbon dioxide and produce oxygen, helping to maintain the habitat's atmosphere. They also provide fresh food, which improves morale and nutrition. Experiments aboard the International Space Station have shown that plants can grow in microgravity. They've successfully grown lettuce, radishes, and even zinnias, a flowering plant, in space. Mars has gravity about 38% of Earth's, so growing plants there should be easier. But there are challenges. Martian soil contains perchlorites, toxic compounds that must be removed before the soil can be used for agriculture. These compounds are harmful to humans and can inhibit plant growth. The soil also lacks organic matter and beneficial microbes, so the crew will need to either import soil from Earth or process Martian soil to make it safe and fertile. They'll also need light. Mars receives less sunlight than Earth, about 60% less on average, and the greenhouse may need supplemental lighting, especially during winter or dust storms. These storms can block sunlight for weeks, as seen in the 2018 global dust storm that ended the Opportunity rover's mission, and they'll need water. Growing food requires a lot of water. A single tomato plant needs about 20 litres of water to produce fruit. The crew will need to recycle water efficiently, capturing moisture from the air and waste and using it to irrigate crops. The greenhouse itself will be a marvel of engineering. It must be pressurized to protect crops from Mars's thin atmosphere, which is 100 times thinner than Earth's. It must also shield plants from harmful UV radiation, as Mars lacks a protective ozone layer like Earth's. Temperature control will be critical. Mars's surface temperature can drop to 80 degrees at night, far below the freezing point of water. Heating systems and insulation will be essential to maintain a stable growing environment. The greenhouse will likely use aeroponics or hydroponics, systems that deliver nutrients directly to plant roots without soil, reducing water usage by up to 90% compared to traditional farming. These systems have already been tested in space, with NASA's veggie plant growth system aboard the ISS demonstrating successful harvests. It's a complex system, but if it works, it could significantly reduce the mass of supplies that need to be brought from Earth. For instance, growing just 50% of the crew's food on Mars could cut the resupply payload by hundreds of kilograms, freeing up space for other critical equipment. But even if we solve the technical challenges, there's one last hurdle, the most unpredictable of all, the human factor. What if the greatest threat to a Mars mission is the crew itself? Section 7. The human factor. A Mars mission will test the limits of human psychology in ways never before encountered. Crew members will spend at least 9 months confined in a cramped spacecraft hurtling through the void and then another 500 days isolated on Mars. The stark reality of this scenario includes unavoidable stress, interpersonal conflicts with no escape, and a sense of isolation that is difficult to comprehend. Studies from the International Space Station, ISS, and Earth-based isolation simulations such as the HIC's Hawaii Space Exploration Analog and Simulation missions have identified key psychological risks that astronauts will face. These include depression, anxiety, interpersonal tension, and cognitive decline due to chronic stress, sleep deprivation, and the insidious effects of radiation exposure on the brain. For instance, astronauts on the ISS have reported feelings of detachment, irritability, and difficulty concentrating after prolonged missions. NASA and other space agencies have developed comprehensive support systems to mitigate these risks. These include pre-mission conflict resolution training, regular counseling sessions during the mission, and even care packages sent from Earth. However, Mars missions introduce unique challenges, such as communication delays of up to 24 minutes, making real-time conversations with mission control impossible. This delay will amplify feelings of isolation, as crew members will be forced to rely on their own problem-solving abilities without immediate guidance. The vast distance, up to 400 million kilometers, will separate the crew from everything familiar, with Earth appearing as a faint blue dot in the Martian sky, a stark reminder of their solitude. To combat this isolation, researchers are creating innovative tools for crew self-support. For example, a computer-based therapy program will guide astronauts through problem-solving techniques and cognitive behavioral therapy exercises. This program, designed to be user-friendly and accessible, will help crew members manage stress and maintain mental well-being. Additionally, a cognitive assessment tool will allow astronauts to monitor their mental state, tracking changes in mood, performance, and decision-making abilities. This tool will provide critical data for both the crew and mission control, helping to identify potential issues before they escalate. Ultimately, the success of the mission hinges on selecting a resilient, adaptable, and compatible crew. The selection process for a Mars mission will be extraordinarily rigorous, involving extensive psychological screening, team-building exercises, and stress simulations designed to push candidates to their limits. The Mars 500 project, where 6 volunteers spent 520 days in a mock spacecraft, offered critical insights into the mental resilience required for such missions. Participants in Mars 500 experienced significant psychological challenges, including sleep disturbances, mood swings, and interpersonal conflicts. However, the project also demonstrated the importance of team cohesion and individual coping strategies in overcoming these obstacles. Future Mars crews will likely undergo even more stringent evaluations, ensuring they possess the emotional and psychological fortitude to endure the mission's demands. Even with the right crew, the risks of a Mars mission are profound. Astronauts will face known and unknown dangers millions of miles from home, with no possibility of rescue. The Martian environment is unforgiving, with extreme temperatures that can drop to 125 degrees Celsius, 195 degrees Celsius at night, and rise to 20 degrees Celsius, 68 degrees during the day. Dust storms can engulf the planet for weeks, obscuring the sun and plunging the surface into darkness. Radiation exposure, both during the journey and on Mars itself, poses a significant health risk, increasing the likelihood of cancer and other long-term health issues. The Martian soil is toxic, containing perchlorates that could harm human health if inhaled or ingested. Despite these challenges, the allure of Mars endures, embodying humanity's greatest ambition to explore the unknown. The preparation for a Mars mission extends far beyond technology and psychology to encompass ethical and philosophical questions. How will decisions be made in life or death situations? For example, if a crew member becomes critically ill or injured, who will decide whether to attempt a risky medical procedure or prioritize the safety of the remaining crew? What if a crew member wants to abandon the mission, potentially jeopardizing the entire endeavor? These questions lack easy answers but must be addressed before the mission begins. The human factor is about more than survival. It is about purpose. Why are we going to Mars? What does it mean for humanity to extend our reach beyond Earth, and what will we discover about ourselves in the process? Observation. The psychological challenges of a Mars mission are as daunting as the technical ones. Astronauts will face prolonged isolation, stress, and uncertainty, compounded by the knowledge that they are completely alone in a hostile environment. The success of the mission will depend not only on advanced technology, but also on the crew's ability to maintain their mental health and work together under extreme conditions. Speculation. It is possible that the psychological toll of a Mars mission will be greater than anticipated, despite extensive preparation. The unpredictable nature of human behavior under stress, combined with the unique challenges of Mars, could lead to unforeseen conflicts or breakdowns. However, the resilience of the human spirit, as demonstrated in countless extreme environments on Earth, suggests that with the right training and support, crew members can overcome these challenges and achieve their goals. Mars will challenge us in unpredictable ways, but every obstacle is an opportunity to learn and grow. When the first crew sets foot on the red planet, they will embody our collective aspirations to explore, discover, and understand our place in the universe. The human factor is the mission's heart, and it will define its success. As they stand on the Martian surface, looking back at the faint blue dot that is Earth, they will remind us of our capacity for greatness, our insatiable curiosity, and our enduring hope for the future. Section 8. The first step. When will Mars missions become reality? SpaceX's Elon Musk aims for 2026 for the first uncrewed Starship mission to test its systems. Success could lead to cargo missions in 2028, delivering supplies for human exploration. Starship's 100-ton cargo capacity could revolutionize efforts to establish a sustainable Mars presence. The first crewed mission is targeted for 2030 or 2032, marking a historic milestone. These timelines, though ambitious, face skepticism. Experts warn of inevitable delays due to the complexity of building and certifying systems. Even with delays, humanity could reach Mars within 20 years, an extraordinary feat. Starship's fully reusable design could cut launch costs by up to 90%, enabling frequent missions. Mars poses formidable challenges, including temperatures as low as 195 degrees Celsius, 126 degrees Celsius, and global dust storms. Crewed missions will rely on untested technology to survive. However, the potential rewards are immense, offering insights into Mars's past habitability and Earth's future while inspiring new exploration. Observation, charta, interpretation, speculation. Achieving these milestones would signify a technological triumph and cultural shift, making humanity a multi-planetary species. While bold, this vision is attainable. The question is not whether it's possible, but when it will happen, and who will lead the way. Section 9. The long view. Going to Mars is within reach. The technology is either here or in development. SpaceX's Starship, a reusable super heavy lift launch vehicle, is advancing through tests, approaching orbital trials and eventual operational status. At 120 meters tall, it could carry up to 100 tons of payload to Mars, enough to transport habitation modules, supplies, and rovers necessary for long-term exploration. Navigating to Mars is well understood, with orbital mechanics refined through dozens of robotic missions like Pathfinder, Spirit, Opportunity, Curiosity, and Perseverance. These missions have revealed Mars's geological history, water ice reserves, and even organic compounds, hinting at the possibility of past or present microbial life. Landing on Mars is achievable. Supersonic retropulsion, demonstrated by SpaceX's Falcon 9 rockets, can slow descent in Mars's thinner atmosphere and lower gravity, a technique that will be crucial for landing Starship on the red planet. The Mars Oxygen In Situ Resource Utilization Experiment, MOXIE, has successfully converted Martian CO2 into oxygen, a critical step for human exploration, producing enough oxygen to support astronauts and fuel return missions. Scaling this up is an engineering challenge, not a scientific one, with systems like MOXIE 2.0 already in development to produce up to 2 kilograms of oxygen per hour. Crew protection from radiation is advancing, with improved shielding materials like hydrogen-rich plastics and medical countermeasures being researched. Growing food in space is possible, proven by experiments on the ISS and advanced hydroponic systems in development such as NASA's Veggie Plant Growth System, which has yielded lettuce, radishes and even sunflowers in microgravity. The uncertainty lies in integrating these technologies into a reliable, safe system. The first crew will face known dangers like radiation and unknown risks like psychological stress. Mars is extreme conditions with temperatures dropping to 195 degrees to 126 at the poles, and dust storms that can engulf the planet mean astronauts must solve problems independently. This mission is humanity's most ambitious endeavor. A century ago, lunar travel was fantasy. 50 years ago, Apollo 11 made it reality. Now, Mars is the next horizon, with private companies like SpaceX and government agencies like NASA collaborating on shared goals. The question is not whether we can go, but when and how well we prepare. Observation, interpretation, speculation. Successful Mars mission could mark humanity's transition into a multiplanetary species. However, the challenges are immense, requiring unprecedented cooperation and investment. The potential benefits, a backup plan for humanity, technological innovation and scientific discovery, are profound. The journey will be perilous, with physical and psychological challenges during the 6 to 9 month trip and harsh conditions on Mars, where the thin atmosphere offers no protection from solar radiation. Yet, Mars's unique landscape, with its vast canyons, towering volcanoes and frozen water reserves, offers a glimpse into Earth's own past and future. The red dust of Mars may hold the keys to understanding the origins of life in our solar system. The journey to Mars is about more than reaching a destination. It's about pushing boundaries, inspiring future generations, and proving human resilience and ingenuity. As Carl Sagan said, somewhere, something incredible is waiting to be known. That something might await us on Mars, whether it's evidence of ancient life, resources for future habitation, or a deeper understanding of our place in the cosmos. The first footprints on Martian soil could redefine what it means to be human, opening the door to a future where Earth is just one of many worlds we call home. Section 10. The Final Countdown. For millennia, Mars has captured human imagination. Ancient civilizations tracked its motion and honored it as a god of war, but now we see it as a frontier, a world within reach. Soon, human footprints will mark its rust-red surface, enduring for eons as a symbol of our ambition and ingenuity. This endeavor is more than a technical achievement. It represents our collective drive to survive, innovate, and cooperate in the face of the unknown. The first Mars-bound crew will confront unprecedented hurdles. 9 months of isolation in tight quarters, bombarded by radiation, and the psychological weight of being millions of miles from home. Yet they'll witness Earth shrink to a distant blue speck and watch Mars grow from a pinpoint to a world of glistening polar caps and endless deserts. Their descent